Okay, so in this problem, we are looking at a cannonball that is launched from a pirate ship at an initial velocity and at an angle above the horizontal. In part A, we're asked how fast is the cannonball traveling when it smashes into the mast of the merchant ship, which is a vertical wall, essentially, that the cannonball is crashing into. So in this problem, a couple things to note that I already wrote here is this is not a level flight problem, so we're not able to use the pre-made range formula, for example. We have to consider more about the problem. And also, unlike most projectile motion problems, this projectile's time in the air is restricted by its horizontal position because most projectiles crash into the ground and that ends their time in the air. However, this projectile is crashing into the mast, a vertical obstruction. So that's going to set its time in the air. I've drawn a picture here that shows the cannonball being launched out of a cannon at the given angle. Define the positive x-axis towards the right and the positive y-axis upwards. I've indicated that the range is given at 65 meters, and of course we're trying to solve for this value here, which is the height. Okay, well actually we're trying to solve for how fast it's going, so not the height that could potentially be solved for. Okay, so what we need to do here is set up and solve for the time of flight. So solve for time of flight, which I will call T sub f, and that is time in the air. Okay, and this is going to be step 1, okay? And I did write that above as well. Okay, so to do that, we have to consider motion in x. So we've got x equals x initial plus v naught sub x times tf, and then plus 1/2 acceleration in x tf squared. Okay, well, there is no acceleration in x. This is a true projectile where it's only being acted on by the influence of gravity, and we can define our initial position as 0. So then we can see that our equation simplifies to simply 65 meters, because that's our given total horizontal distance, equals the initial horizontal component of the launch velocity. So that would be 45.8 meters per second times cosine of 25.1 degrees. Okay, and then we're going to that's going to have our variable tf, and now we can simply solve for the time in the air. Okay, so the time in the air, okay, so we'll plug this in. So we have 65 meters, okay, and then we are dividing, okay, by 45.8 times cosine of 25.1. Okay, so we'll put this in parentheses here. Okay, so 45.8 and then times cosine of 25.1, and my calculator here is already in degree mode. Okay, so close both the parentheses. Okay, and so I get a time in the air of 1.42 seconds, rounded to 3 sig figs, 1.42 meters per second. And now we're going to take that time and plug it into the velocity to find how fast it's traveling when it smashes into the merchant ship, okay? And we're going to find both components of its velocity and then take the resultant of the two components using the Pythagorean theorem to find the total speed that it smashes in. Because here it just says, how fast is the cannonball traveling? That right there implies it doesn't want a particular component of the final velocity, just the speed. Okay, so I have Vx and Vy. Okay, so we're going to take both of those components. So in x, well, it's simply V naught x. Nothing has happened. Okay. In y, we're going to have, it is going to be V naught y, and then minus 9.8 meters per second squared times t flight. Okay. Okay, so for Vx, we can take the value of just the x component of velocity, which is just the 45.8 multiplied by cosine of 25.1. Okay, So just that value on its own gives us 45.7. Okay, so that is just the x component of the initial velocity. And I'm going to check that, make sure I'm in the correct mode here. Nope, I was in degree mode. I noticed that because my values were off, so I'll fix the other value as well. Okay, so let's go ahead and exit this. Okay. Okay, so let's go back up and recalculate this with the correct angle. Okay, so that's going to give me 1.56 seconds. So not a big change to the time, but you'll notice there will be a more significant change to the component now that we've corrected our mode on the calculator. Okay, and that's going to give me 41.5. Okay, so I have 41.5 meters per second. Okay, and then for the x component, okay, well, I'm going to expand this out just a little bit because we haven't seen it yet. It would just be 45.8 meters per second times sine of 25.1 degrees. And okay, and then of course minus 9.8 meters per second times our solved for time of flight of 1.56 seconds. Okay, so we're going to take this component here, change it to a sine. Okay. And then minus, all right, 9.8, multiply that by 1.56 seconds, which was the time up here. And we're going to take it in the calculator, so we're not doing any intermediate rounding. All right, and so we get the velocity of 4.07 meters per second in the y direction. Okay, so interestingly, this does tell us that the y component of the velocity has gotten quite small. So kind of as I drew it in the picture, we are near the top of the arc when the cannonball smashes into the mast, because at the very top, the y component would be 0. So the overall magnitude of the velocity, or the speed at which the cannonball crashes into the mast, can be found by taking the square root of the sum of the squares of the two components, like so. And so then the number we're going to get is just going to be 41.5 meters per second quantity squared plus 4.07 also squared, and all inside the square root. So we'll use the calculator to do this. So we'll take the square root function, and then we're going to get our x component here, and we're going to square that so that we can get this all worked out. Okay, and then we will add the y component as well, also squared. Okay, so that gives me 41.7 as the final speed. Okay, so that is our answer to part A. And let me just resize this so we can quickly answer part B as well, which is a nice follow-up to A and will only involve taking the inverse tangent. Because we're trying to find the angle at which the cannonball hits the mast. So if we were to look at the two components, essentially, so or exactly, because if we have the velocity, and I'm going to kind of draw it in over here to what it might look like. So obviously it's much, much bigger in the x direction. It has a small y component. So this is the velocity, not the initial velocity, but the velocity at which the cannonball strikes the mast. And this, of course, is not exactly to scale, but there we have our two components. And this is on here, BVX, which is the 41.5, and about 10 times smaller is VY. Okay, and they're both positive, which tells us that the angle that we're going to be solving for is going to be above the x-axis. Okay, so then I'm going to go ahead and find theta. I'm going to say that theta is tangent inverse of Vy over Vx. Okay, and that's just taking the definition of tangent. And so that's just going to be tangent inverse of 4.07 divided by 41.5. Okay, units cancel because we should just get something that's in degrees. Okay, so here we will go ahead and work that out. So tangent inverse And we'll take the x component, and then we're just going to divide by the y component. So that's a great thing about having these in your calculator. You can just refer back to them in a lot of these type of vector problems. Okay, close the parentheses. All right, so we get 5.6 degrees. Okay, so that's 5.60 degrees and above horizontal. Okay, so that is the problem of projectile motion, but with a restraint on the motion in x rather than a restraint on the motion in y. Thank you.